Okay, grade 12's everything that you need to know about probability. I know that you guys didn't do probability last year, so I'm combining both the grade 11 work and the grade 12 work in one video. I'll tell you when the grade 12 work starts, okay? So, probability, and you guys have been doing this since we were in grade 8 and 9, it's in your syllabus there. We spoke about probability as being the number of successful outcomes over the number of possible outcomes. Okay, now what I'm going to do is I'm going to demonstrate exactly what I mean and how we would teach it to you guys when you guys were in grade 8 and 9 to understand exactly what's happening. Okay, so this is what I'm doing, okay? And for anyone that has noticed this thus far, you know how much I love my stationery. We're going to use my stationery to demonstrate what I'm talking about. So I lined up a couple of my pens over here. I've got 2 yellow, 1, 2, 3, 4 green, 1, 2, 3, 4 blue, 5 blue, and 2 purple pens. The ones they included, okay? This here is the number of possible outcomes. What did I say? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 number of possible outcomes. Okay, just shift this up and show you guys what I'm talking about here in the formula for probability. This here, this possible events, okay, or the denominator of this formula is the amount that we have in total. The number of successful events has to do with each of the scenarios that we give you, okay? So if I ask you right now, what is the probability, let's move this all together, right? What is the probability of me pulling out a purple pen from the set over here, okay? Now, in order to do that, we know that we had 2 possible purple pens, right? So the probability, let me get a scrapper to scribble here. This note that you see over here, I already scanned it and I put it in a group for you guys, okay? So the number for this particular data set over here, probability of purple is equal to 2 out of the 13. Okay, that's what you needed to do. If I asked you from this set over here, what's the probability of pulling out a blue pen? It would be probability of blue. We said there were 4 pens, am I right? No, 5 blue ones. 1, 2, 3, 4, 5, right? Which is 5 out of 13, okay? Now that is the simple stuff. We then went on and we spoke about probability of pulling out a blue or yellow pen, okay? Now in my data set over here, I had 13 pens. How many of them are blue and or yellow, okay? And that there would be the 5 blue pens, 5 blue pens and 2 yellow pens. So let's write this down. Probability of blue or yellow is 5 plus, what did I say? Got distracted. 5 plus 2, 7 out of the 13. Okay. If I asked you for probability of blue, no, let's use a different color. Purple or green. Probability of purple or green. In total, how many purple and how many green did we have? 1, 2, 3, 4, 5, 6. So 6 out of 13. And you would notice something very important, and I wrote it down over there. This here, whenever we have an or, okay, this here is called a union, and it's represented by this over here, okay. This here, you would notice that I keep using the plus sign, and I'm going to explain it when I do the tree diagram as well, and I have it written down over here in this note. It's the union. What happens when you see the word or in probability, it implies an addition. So here, for this one, the 7 out of 13, in order to get that 7 out of 13, we said the 5 out of 13 plus the 2 out of 13. That's what we did, okay? And if we wanted to do purple or green, we said the purple, which was 2 out of 13, plus the green, which was 4 out of 13. So remember this. If you see the symbol like this, it means union, okay? And it's addition. Anytime you see the word or, it's addition. Very important. Okay, I could have asked you then how many pens are purple and green. Okay, I don't have any pens that are a combination of both of them, but if ever we have an and situation with probability, then this is the symbol given to us. It's intersection, okay, so like a event and B, it means event A happening and B, they're happening at the same time. And when they're happening at the same time, or we have the word and, or we see this intersection, then know that you've got to multiply your two fractions. Okay, so for example, I know it's not possible with this, but if I had to do purple and green, it would have been 2 out of 13 multiplied by 4 out of 13, because we said 2 purple pens, 4 green pens. So 2 out of 13 times 4 out of 13. Okay, that's what it is. Very important that you know that. Okay, let's get the pens out of the way. Let's continue. That's as far as you knew in grade 8 and 9. We went a little further, and this is grade 11 content, okay? We spoke about something called mutually exclusive, okay? Mutually exclusive is where one event can happen, but at the same time, let's say that again. One event can happen, but at the same time that event is happening, another event can't happen at that time. Now, what do I mean by that is, for example, a number being both odd and even. At the same time, they can't happen. It's either it's odd or it's even. Another example would be a student taking maths or maths lit. They can't happen. No student at our school can take both maths and maths lit. It's either you're taking pure maths or you're taking maths lit. Okay, that's what mutually exclusive is. Now, because they can't happen at the same time, let's scribble over here, okay? And I'm going to Venn diagrams, and I'm going to explain that in a little more detail in a second. But basically, with mutually exclusive events, let's say this is all the people taking pure maths, there cannot be an intersection over here, and this is an intersection that we represent with a Venn diagram. This cannot possibly happen with maths and maths lit. So instead, you'd have maths happening and maths lit happening. That's a mutually exclusive event. Okay, all right, let's go on. We have complementary events. Now, when we say something is complementary, it means, I forgot to mention this, but all our probability is either between 0 and 1. I think you guys knew that already. It can there's either a 0 chance that it's happening, or 1. Your answer of all of your fraction can be 1, and it means it's a 100% chance that's happening, right? So when an event is complementary, it means 1 minus the probability of it happening is the answer to it not happening. Like, for example, with our maths and maths lit, we were still busy with that one, okay? If I had to work out the probability, if I had to pull out a student at random at Glen Vista High School for someone that takes pure maths, okay, it would be a certain amount. Let's just say out of the 200 students, I'm just picking random numbers, out of 200 students, right, 50 take pure maths and 150 don't take pure maths, right? So the probability of maths is equal to 50 out of 200, and the probability of maths lit is 150 out of 200. Okay, so I was saying I'm pulling someone at random. That's my probability of them being a math student, or my probability of them being a maths lit student. If I had only information about this maths lit situation over here, and I told you that they're complementary, we can work out this probability as well. Because let's simplify this. This here is, oh no, let's not actually simplify it. Let's leave it as it is. Can you see how this one here is 1 minus 150 over 200? If I have to work this out, that's 200 over 200 minus 150, which gives me 50 over 200. That's exactly what I was saying. The probability of this happening is exactly the same as the probability of this not happening. Or the other way around, the probability of this happening is exactly the same as 1 minus the probability of this not happening. That's what I mean. And when we say not, I wrote it down here. Yes, I did. We can either say not A, or not maths lit, or not pure maths, or you can represent it with an A and a dash. And I know that that's a dash being used again there. Very different to what the dash means in calculus. Just be careful with that, okay? All right, let's go on. I wrote here the addition identity. I think you guys have learned this in previous grades. I'm not too sure about that, okay? But anyway, the probability of A or B happening is equal to the probability of A happening plus the probability of B happening, because we already discussed this. When we see the word or, we're going to add it, but then we're subtracting A and B from it. Why on earth are we doing that? Let's show you guys this visually. Let's flip around, okay? Because I keep saying this, we all visual learners. Let's say this is A happening and B happening, okay? So they are not mutually exclusive. It's just any event happening, right? This here is A, this here is B. This part over here is A and B happening at the same time, okay? So the probability of us choosing something within these two circles would be me adding this first circle, would be everything in this circle over here, plus everything in this circle over here. But you agree with me that we'd add this part over here twice, because it got added in the first circle and it got added in the second circle. So we just have to take out one of it so that it's not clashing. And that's why we have this formula over here. A plus B minus the A plus A and B happening at the same time. Okay, that being said, if it was a mutually exclusive event, remember we said A and B are not happening at the same time. No maths and maths lit, for example, right? So do you see this A or B will just be probability of A plus probability of B, because this part over here is basically 0. That's what's happening over there. Okay, let's move on to Venn diagrams. Now, I already drew Venn diagrams for you, but basically Venn diagrams are used to represent things and make it a bit easier for us to see things visually, okay? Now, you might possibly get a question like this in your probability section, okay? Let's quickly just talk about the types of probability questions we can ask you. We can either ask you a Venn diagram, we can ask you a tree diagram, we could ask you a contingency table. I'm going to go through each one of these. We can also possibly ask you to just substitute into this formula, the addition identity, okay? Then we go on to the grade 12 stuff, which has to do with counting principle. So those are your possibilities, okay? Hope I didn't miss anything. No, I didn't. Okay, so this here, I already spoke to you about it. This means event A and B happening. I told you this middle part over here is the intersection where they happen at the exact same time. And this here is the formula. We already discussed this, okay? If they're mutually exclusive, and we discussed this part as well. What's happening with the mutually exclusive is there's no intersection between them, and because there's no intersection between them, the A and B, the probability of A and B happening at the same time is equal to 0. Therefore, the addition identity, and I literally just repeating what I said a few minutes ago, the addition identity has basically this part here as 0. Okay. With your Venn diagram question, okay, you can get one of two types, okay? One is where we're going to give you the numbers in decimals, okay? Something really simple like probability of A plus is equal to something, probability of B is equal to something, and stuff like that, like how I have in this document, okay? That's the one possibility. The other one, they might give you a little more real life explanation. They'll tell you, I seen this one a couple of years back. They said from a group of students at school, some of them are using Twitter, some of them are using Instagram, some of them are using WhatsApp, okay? Some of them are using Instagram and WhatsApp, some of them are using Twitter and Instagram, and some of them are using Twitter and WhatsApp. And then there's said that there's a few of them that are using all three of the apps, okay? If you didn't follow what I said, just scroll back a little and listen again to what I'm saying. But basically, they gave you some information there. They gave you some numbers in some of them, and they gave you some things that were unknown. And they wanted you to draw a Venn diagram with that. And that's what I have here. I said, when you're drawing your Venn diagram for that, start with the and part, and then move your way outwards. So that part where I said the people that are using Twitter, Instagram, and WhatsApp, that's an and part. Let's scribble this down, okay? I didn't actually do an example of that in here. But if you guys would like, and you find one of those and you don't understand how to do it and you want me to do it, please send me a message and I'll make a video out of that. But basically, here's the Twitter people, there's the WhatsApp people, and there's the Instagram people. This part over here is where I want you to start. You start in the middle with whatever information is given to you. If they tell you it's unknown, write X. If they give you a number, write that number down in the middle. And then if I tell you the Twitter and WhatsApp people, okay, the Twitter and WhatsApp people includes this whole part over here. All right, don't forget that, say I told you that this middle part over here is 5, and I told you that I shouldn't have written that there, but it should be there in the middle, right? Let's say I told you that part is 5, and I told you the Twitter and WhatsApp people are 10. Okay, how would you figure out what number goes into this part here? It should be the 10 minus that 5, because that 5 is included in this little ovally shape over here. So be careful with that kind of stuff as well. If I then told you that the WhatsApp and Instagram people are 20, you're going to say 20 minus the 5 here would be 15. Okay, if I told you the Twitter and Instagram people are 30, for example, you're going to say 30 minus that 5, giving you 25 over there. Okay, be careful with stuff like that. If I told you in total, okay, so this part here is 5, that was 5. In total, I told you this whole part is 70. Okay, how would you calculate what goes into this part? You'd say 70 minus 25 minus 5 minus 5, and you'd get your number over there. Okay, that's what I mean by start in the middle and work your way outwards. All right, sometimes we might give you, I already mentioned this, an unknown. If I told you that this middle part is unknown, then your thing here would have been 30 minus x. Your thing here would have been 10 minus x. Your thing here would have been 20 minus x. And then the same thing for this one here, you would have said 70 minus x minus that, to simplify whatever this part is, and this part and this part as per the information. Don't forget that there might possibly be people in this situation here that don't use Twitter, WhatsApp, or Instagram. Where would you put that information? You'd put it somewhere over here. It means it doesn't fit within those circles. So they're here inside. They're still part of our data set. Okay, so you'd put them still in your rectangle, square, whatever it is, right? But they're just not part of our circle, so you put them over there. Okay, you write an S over there. It means the sample space. And do not forget that everything in the sample space has to add up to the total that were questioned, whatever. So if I told you that this year were 140 children, the total of this plus 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 the people here must add up to 140. And you can use that when they ask you the one where they say something is unknown. So you'd add this and 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 this equals to 140 and solve for the unknown x. I think I repeated myself a couple of times there. But anyway, let's move on. Okay, here I have a couple of questions. Like I told you, the one possibility, a very colorful page. As you can see, I was having fun with all of my colorful markers. But anyway, you might see a question exactly like this in the test. We might not always tell you to use a Venn diagram. If we tell you to use a Venn diagram, then know that there's going to be marks for it. If we don't tell you to use a Venn diagram, there isn't going to be marks for it, but you can, and I advise to use a Venn diagram. I keep saying this, most of us are visual learners. It makes it so much easier if you just draw something out rather than just read these words over here to get the answer. Okay, this one here says we're given this information, so event A happening and event B happening. Event A happening, so in total, this whole circle of event A happening has a probability of 0.3. And in total, the whole thing of B happening has 0.7. Okay, then you have a probability of A and B happening at the same time, being 0.2. Right, we did not know what this amount is, and I'm going to show you how I calculated it. The thing said, first draw a Venn diagram to represent the information, then compute or total up or calculate the value of probability of B happening and probability, and no, wait, let me say that again, probability of B happening and not A happening. So it could be written like that, or it could have been written like this. B and not A. That's what we're looking for. Okay, now I filled in all of the information. Let's talk about the information being filled in. I started at the middle. I told you to always start at the middle with the and part, so I filled in this part here first. Okay, and then I took the 0.3 over here of A, minus this middle part to give me the 0.1 over here. And I wrote the calculation for you in case you wanted to know. And to get the 0.5, what I did was I took the 0.7 because I know that the whole circle of B means 0.7. So 0.5 plus the 0.2 gives me the 0.7. Does that make sense there? 0.7 minus 0.2 giving me the 0.5. Okay, and then I just double checked in case there might be something outside. Okay, so what I did was I said 1 minus the 0.1 from here, minus the 0.2 from here, minus the 0.5 from here. Okay, because I know everything has to add up to 1, and it gave me 0.2. So that means 0.2 is not in the circle. Okay, then I needed to ask myself, where is B happening and not A happening? Now you agree with me that this whole circle is A happening, so everything that's not in this circle would be not A happening. So that would be all of the pink part happening and everything around it, so including the 0.2. But they were very specific with the condition. They said B happening and not A. So that means we can exclude this part over here because during or in between the 0.2, B is not happening. So our answer lies in just this pink part over here because B is happening in that part and not A is happening in that part. And then I just wrote my answer, 0.5, and I told you it's marked in pink in case, yeah. All right, or for the people that are not watching this video and they want the information, that's what it's for. All right, given the information, probability of A is 0.5, probability of A and B is 0.2 this time, and probability of not B, okay, so that means that everything that's not in the B circle or doesn't form part of the B circle is 0.6. Interesting. Draw a Venn diagram to represent this information and determine the OR part, okay? All right, how do we do this? So here's my Venn diagram. I am told 0.2 is the middle, the end part, okay? I am told 0.5 is the probability of A, so that means everything in the circle of A should add up to 0.5. So I took 0.5 minus the middle to give me that part, okay? And then I am told 0.6 is the not B part, okay? And then I have a whole calculation here color coded in blue. I said the total probability of anything happening in any event is 1. 1 minus the 0.6 is 0.4, okay? Because we know that if something is, oh wait, let me say this again. Wait, I lost my train of thought. Okay, sorry. Probability of B is the same thing as 1 minus probability of not B. That's what I did over here, 1 minus the 0.6, right? So that gives me 0.4. 0.4 is everything that is B. Then I said A and B is 0.2, this part over here. So the 0.4 minus the 0.2 of this middle, therefore it gives me this part as 0.2, okay? That's what I wrote here. This means probability of B on its own is 0.2. Okay, there we go. Then the probability that might not be inside, oh, I forgot to write an S over here because sample space. The probability of the people or the things that are not part of this event A or B, this is that 0.3. How did I calculate it? Remember, we know the total. 1 minus the 0.3 from there, minus the 0.2 from there, minus the 0.2 from there, and it gives me 0.3. That I know goes outside. Now I said I want probability of A or B. That means anything that's highlighted in orange, because that's A or B, okay? Or you could have done it if you wanted to using the identity, okay? But anyway, I just added 0.3 plus 0.2 plus 0.2. And it gives me 0.7. You could have done it that way. You could have also just said 1 minus the 0.3 because, I mean, if the whole thing is 1 and 0.3 doesn't lie within it, then obviously that's 0.7. Right. Third example, now this one here is with percentages. Percentages can be turned into decimals. Don't forget, you just divide by 100. So we have a study undertaken to see how many people in PE owned a VW or a Toyota. 3% owned both, I changed it over here. Here's it color coded for you, 0.03. You could have left it as a 3%. That's perfectly fine. All right. It's just I got familiar with using the decimals. So I went back to decimals. 25% owned a Toyota. So that means this whole thing over here should be 25%. I changed that to 0.25 and I subtracted the 0.03 from it because I want just the pink part, and there we go, 0.22. And 60% owned the VW. Again, I forgot to write the S for sample space. 60% owned the VW, and so that was 0.6 minus the 0.03 to give me 0.57. I then just needed to calculate how many owned neither of them. And to do that, I said 1 minus the 0.22 minus the 0.03 minus the 0.57. Here's my calculation over here. And it gave me 0.18. Okay, and that's exactly what they wanted. They wanted what percentage owned neither car. I just needed to turn my decimal back to a percentage. So I multiplied by 100, and there's my percentage. Okay, and now we're talking about independent events. So this is another identity that you need to know. And with these independent events, most of the questions then follow up from it and they talk about a contingency table. If I'm not mistaken, I think the bio students, you guys talk about contingency tables. Can't remember so clearly, didn't do bio, but I think you guys have a contingency table. But anyway, this is what the identity is for independent events. Now let's quickly recap on what does the word independent mean. It means that if one event is happening, the other one doesn't necessarily happen because of the first event happening. That's what it would mean. So with event A and B, if the A and B part, okay, if you work out whatever the probability of them happening at the same time is equal to exactly the probability of A multiplied by the probability of B happening, then those two events are said to be independent. And obviously the opposite of this would also be true. If this here were not equal to each other, they'd be dependent. Okay. All right, now with the contingency table, that's pretty much what you need to know with the identity. With the contingency table, we summarize information for you. Okay, so this example said we are conducting a survey on a whole bunch of people, 140 people to be exact, okay, and we categorized whether they were 35 years and younger or older than 35 years. So that's what we have over here. So 80 of them were 35 and younger and 60 of them were older than 35 years. That's how we got the 140. From there, we asked them how many of them preferred tennis, how many preferred running, how many preferred gym. I think with this thing over here, it was you were only allowed to choose between tennis or running or gym. You couldn't choose all of them at the same time. Okay, now they give you some unknowns in this particular table. Sometimes they ask you to solve for the unknowns. This question only wanted us to solve for A. But sometimes after they make you solve for A, they can tell you then find B and then find C and find D, and which is pretty easy. If I have A, you can work out C by saying 80 minus the 28 minus the whatever the answer of A is. I think this question actually made us work out C, but anyway, we'll get there. And if I wanted D, you'd do the same. B, you'd do the same thing over here, and yeah, like that. If you see each one of these numbers, this plus this gives me that. This plus this would give me that. This plus this gives me that. This plus this would give me that. If I add this plus this plus this, it gives me that. This plus this plus this gives me that. Now, how is this important to what we need to be doing? We are told over here in this question, if it is given that preferring to play tennis and age are independent, so we know automatically, okay, that the probability of this happening multiplied by the probability of that happening is not the same as the probability of the, is equal to, there we go, equal to the same thing as this happening. That's what we know. They are independent of each other, determine the value A. It's exactly what I said. We're going to set up an equation using this identity. So what I did was I said probability of tennis, color coded it for you. It's all of these people that like tennis multiplied by the probability of the yellow one, 35 and younger, right? There it is over there. And we want to see if it works out, or we're going to say is equal to the probability of A happening. The probability of tennis is 21 out of 140. Probability of 35 and younger is 80 out of 140, and probability of A happening is A out of 140. Now this here was my whole explanation to what I'm getting, and this is the actual calculation, what I just said. You multiply and you solve. We could ask it to you the other way around. We could give you this value and we tell you prove if this is independent or dependent. You would do the exact same thing, but just remember, when you're proving something in a calculation, you're going to have a left hand side and you're going to have a right hand side, very like separate. You're going to see that your answers are the same, and if they were the same, they are going to be the same. Then in this case, then you're going to say that they are independent. If they're not the same, if the two fractions on either side are not equal to each other, then you're going to say therefore they are dependent. Okay. My question then says, they have given you that it's 12. Determine the probability that a randomly selected person prefers going to the gym or is in the age group of 35 and younger. Okay, so prefers going to the gym, this one over here, and is 35 and younger. So we basically just want to do C out of 140. So we're going to calculate C by saying 80 minus 28 minus 12. Let's see. There we go. I calculated C, it was 40. Now remember, when we see the word or, please don't forget it's addition. Okay, and in this particular case, because we're using that addition and we see the word or, we're going to use the addition identity. So the probability of going to gym or being younger than or equal to 35 is the same as gym plus being younger than or equal to 35 minus the people the gym and the younger than and equal to 35. It's basically the situation we add in all of the A plus all of the B minus that one there, because it got added twice. Right, which is exactly what I did. I took the values here for gym. I took the values here for what was this, younger than and equal to 30, minus the people that are both liking to go to gym and being younger than and equal to 30, and I substituted and calculated, and that was the answer. Tree diagrams. Okay, now with tree diagrams, this is something that you were supposed to be taught properly in grade 11. Okay, I'm going to go through this really quickly. I was supposed to make one full video for you guys, but I'm sorry, my phone is dying. So we're going to make two separate videos, one with grade 11 content, one with grade 12 content. Tree diagrams. What you need to know about this is that as we're moving across the branches like that, we're going to multiply, okay, because it means something happening and something else happening. And as we move down, okay, so something happening or something happening or something happening, we're going to add. Okay, don't forget your identity. So I found one of these questions. It was from the Siavula website. It says that you're rolling a dice twice and you adding up the dots to get the score. Draw a tree diagram to represent all of this. This was a pain to draw this tree diagram. I hope they don't ever ask you one that's so ugly to draw. But anyway, the first time you roll the dice, you have 6 possibilities. So either you can land on 1 or 2 or 3 or 4 or 5 or 6. If you land on 1 and you throw the dice again, you could land on 1, 2, 3, 4, 5, 6. If you threw the first time and you got 2, you could again land on 1, 2, 3, 4, 5, 6. That's what I did with all of this. Okay, and that's why I said it's a pain to draw, because as you can see, it looks so messy and ugly. Okay, now for the probability in this particular question, we know that the probability of getting 1 on a dice, and we're assuming that this dice is perfectly weighted. You do know that you can get a dice where it's heavier on one side, and because it's heavier on one side, it's going to land on that bottom, and then the other side would be displayed, right? Play around with the dice and try and understand what I'm meaning with that. But anyway, we're assuming that this one over here is evenly weighted. So the probability of getting a 1 is 1 out of 6. A 2, 1 out of 6. 3, 1 out of 6. Same thing for this one's over here. It was the same dice. Other times, in other situations with the tree diagram, we might tell you different scenarios, okay? So the probabilities might be a little different. The things that you do need to know: for a dice, 6 sides. So if it's evenly weighted, then it's all 1 out of 6. If it was a pack of cards, you should know that there's 52 cards in a pack, and each one of those things will have 13, right? So there's 13 aces, 4 of each one, and 13 of the different symbols. Okay, so there's that heart and the club and the diamond, and what am I missing? I can't remember what I'm missing. The spear, I think it was, right? There's 13 of each one of those, and there's 4 of each different number, or king or queen or jack. Okay, don't forget that. That's important to know. All right, as we're moving across, so if I want to know what's the probability of me getting a 2 and a 5, it would be 1 out of 6 times 1 out of 6. So as we're moving across like this, it's and, so it's going to be multiply. I took the time and I wrote out all the different possibilities for us, and I even added them because it said you add in the dots, adding up the dots to get a score. So if you got 1 the first time and 1 the second time, you'd get 2 in total. All right, that's what I did. And then I worked out the probability. I wrote it here. I said each one of them, I just explained this, it's 1 out of 6 times 1 out of 6. This one here says, what's the probability that your score is a multiple of 5? That's what I highlighted, all the ones that are multiples of 5, which is 5 and 10 in this case. There's nothing higher than that. So what's the probability of that? We're saying either this one, or 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 this one. So we're adding each one of them. And because we're adding the exact same number each time, I just went ahead and said 7 of them multiplied by 1 out of 36. I have another example, and then I'm going to end this video, and then there'll be a second one. But anyway, this one here is you throwing a dice and flipping a coin. So event 1 is throwing the dice, and for the dice you could get again 1, 2, 3, 4, 5, 6. Then event 2 is the flipping of the coin. So there it is. You could either write what you're doing, or you can say event 1, event 2, and then outcomes. And then I wrote down all the possible outcomes. So you can either get 1 in head, 1 in tail, 2 in head, 2 in tail, 3 in head, etc. All of them here. And the part that says even number in heads, it's this one, and this one. So remember, to get the answer for 1 in head, it would be 1 out of 6 because there's 6 numbers on the dice, and 1 out of 2 because if you're flipping a coin again, then this here is going to be 2 possibilities. So each one of them is basically 1 out of 12. All right, for this particular question. How many of what's the probability of even numbers? It's going to be the 1 out of 12 plus 1 out of 12 plus 1 out of 12. As we're moving down with the different options, it's addition because it was or, and there's our final answer. And I just recapped over here. To work out probability of each outcome, you multiply. To work out the probability of number of heads, even number in heads, then it would be adding each one of them. Okay, let's stop.